What you are looking at here is the master boot record in its hexadecimal view within a disk editor. It is within a tool such as this that a computer forensic analyst examines files, disk images, and mounted drives. In order to use this tool, an examiner must first understand how to navigate around this environment. Data is displayed line by line, denoted by a value on the left, which is known as an offset. Whenever you need to get to a file or folder's exact location in memory, you navigate to its location in terms of its offset in memory, which can be represented as either hexadecimal or in decimal. When an examiner is searching for signatures or extracting the clusters of data which make up a stored file, he must first understand something known as disk geometry in order to navigate in this environment to find what he is looking for. This lesson will go over the basics of disk geometry and how it applies to navigating in a disk editor. Disk geometry refers to the hierarchical organization of data in the storage mediums that we use. The term geometry is used because the organizational study was first applied to disks. These would be floppy disks and hard disks. Since disks are circular in nature, when engineers designed how information would be systematically organized, it was referred to as geometry. If you get into a much higher level of computer engineering, there will be some complicated math associated with this. But at the level of the general computer forensic examiner, this is not the case. Currently, there are other forms of permanent storage besides hard disks, but the geometry term still applies when it comes to the hierarchy of this storage structure. The most prevalent form of storage media besides hard disk is flash memory. This is what is found in smartphones, thumb drives, digital cameras, and some newer hard drives. Even though these two storage types are different in physical materials and engineering, the file system that Windows currently uses, which is NTFS, applies the same architecture for both. In other words, even though flash memory stores data in pages and blocks, and hard disks store data in sectors and clusters, the file system will refer to data as sectors and clusters. With that thought, let's continue to the next section. The smallest unit of memory is the bit. This is either a 1 or a 0, on or off, the presence of electrical current or the lack of electrical current. The next highest unit of memory is the byte. That is 8 bits. In a disk editor, that is represented in hexadecimal as either 2 numbers or a combination of a number and one of the alphabetic characters A through F. 512 bytes is equal to 1 sector. The sector is the smallest unit of addressable memory in a storage medium. This is the smallest unit of space on a hard disk that any software program can access. By default, 8 sectors equals 1 cluster. Clusters are how the Windows file system stores fragments of files throughout a hard disk. Since a cluster is equal to 8 sectors, it is 4096 bytes in size. The aforementioned sizes are defined by default, however they can be changed. There are a number of applications that will allow a user to alter the settings for the sizes of a sector and a cluster. In some of the much larger storage volumes, 2 and 3 terabytes for example, you might see different sector and or cluster sizes. It is very rare, if ever, that you will find that someone has altered the default sizes of the sector and the cluster. The default sizes of 512 bytes and 4096 bytes are most likely the ones that an examiner will come across. Now that you know the basic hierarchy of how memory is stored, you can begin your navigation around the environment of the disk editor. If you take a look at this master boot record, for example, you will notice that it takes up 1 sector. You can see the offset to the left side of the screen where it says 496. If you start from there and count until you see the 55AA in hex, that will be 512 bytes. By the way, the 55AA is the closing signature for the master boot record. One thing that you need to remember is that when you start counting from the beginning of the first offset, that would be the offset listed with all zeros. For example, you would start your count with 0, 1, 2, 3, and so forth. Another thing that you need to keep in mind is that there is a difference between the logical and the physical start of a block. The physical start is in reference to starting at absolute zero, which is the very beginning of the disk. Logical zero will be when a block will start at zero, but it will not be in reference to the beginning of the disk. This would happen, for example, if I was to navigate to the first record of the master file table and start counting from the record's first byte at 0 instead of its absolute offset, or its offset in reference to the very beginning of the disk. If I scroll down in the disk editor until I see a black line, that line marks the end of the first cluster. A cluster equals 4096 bytes. You can see there's a line delineating the end of the first cluster, and then there is a series of E5s from when the volume was first given a low-level formatting. There's another feature of most disk editors that you as examiners will be using quite frequently. That will be the jump to offset or sector feature. Many times when you convert a value from hexadecimal into decimal, that converted value will be a jump value, which will lead you either to a certain physical decimal offset or to a sector or cluster number. Here's an example. This particular jump will take you to a physical decimal offset. This jump tool will take you either to a sector or cluster number. Say, for example, if I want to go to sector number 1, the application has sent me to the 45th sector of the volume. Now that you have a basic understanding of what a sector, cluster, and physical offsets look like at the hexadecimal level within a hex editor, you're ready to do some basic analysis of blocks of memory. Remember that there is a difference between physical and logical offsets, meaning the physical starts at a disk's absolute zero. Also remember to use little endian for extracting hex values when appropriate. This concludes the presentation.